Yep.
Okay, so nonlinear oscillators. So things to talk about is why we need oscillators at all for running. Something as simple as a wheel can be seen as an oscillator. Talk about dynamic system models of oscillators. Simple mass spring damper we'll stick with. Talk about linear oscillators, which I'm sure you've all seen 1,000 times. Nonlinear oscillators, which most of you have seen already. Amplitude dependent resonance. And how to drive these things, and phase driving and other means of driving them. Okay, so why do we need oscillators to run?
Efficiency and power requirements. If you have a leg that's moving back and forth, it needs to accelerate and decelerate frequently. If you're trying to do all of that with a motor and a controller, you're going to just be dumping power into it and need a very powerful motor. If you have an oscillator on it, then it does so with much less energy usage and therefore much less energy waste.
Okay, so those are advantages of using particular types of oscillators. But just in general, you've only got 2 legs, right? So you can use them over and over again. Or maybe with the hex runner you've got 6 legs or whatever. But you've got a finite number of ground contacts that you have to use over and over to get a long distance. So you can have something that goes around in a cycle, right? No matter what. Now, sure, the reason we want to use them in fast runner is efficiency and speed and all that nice things. But in general, to run or to walk, you have to have an oscillator. In fact, you need an oscillator even if you're a wheel, right? If you take a wheel spinning around in a circle and in a pattern looping over and over again, so if you did something like just put a point here and plot the height of that point as a function of time, you're going to get a sine wave, right? The wheel's at constant velocity. So just a point on a wheel is an oscillator. Right. Okay, so it makes sense to talk about oscillators when we're talking about running, whether or not you use fancy spring systems that give you energy savings. Okay, so dynamic systems, and let's just start with spring mass spring damper, because that's, at least for me, the easiest to understand it. Some people might understand capacitors and inductors better and make RLC circuits, which are equivalent to mass spring dampers, or any energy domain, you can make an oscillator. So, well, before we get to that though, let's talk about it. So for dynamic systems, you got some state vector x dot is some function of state x, some input u, and t, right? So how many degrees of freedom do you need to make an oscillator? 1. Heard 2 and I heard 1. So here's one way to make it with 1 degree of freedom. You just have that x dot equals 1 and that y equals cosine of x. Right, so with a dynamic system in general, you have some state vector x and some output vector. Well, if you can put t in here, you need 0, right? You just have that y equals cosine of t, right? If you've got a timer. But let's say you don't have a timer and we want everything to be a function. Don't put t in there. Then you just do the trick, where if you need to create t, you just have one of your state vectors essentially be t, like by just saying x dot equals 1, right? So as you integrate that up, you get time. So you can have an oscillator with a 1 degree of freedom system as long as you have nonlinearities in it. If you have a linear system, then you need to, right? Because any linear system, if you just have x dot equals ax, all that can do is either blow up or decay to 0. In order to oscillate, you need something that looks like a mass spring damper. If you have a mass on a spring, a damper, and some driving force F, then your equations are going to be F equals ma, mx double dot equals, if you have spring constant, well, let's just say that's a general purpose spring. So it's going to be some restoring, I'll put the negative there just so that it's restoring, some spring function of x minus some damping function Yeah, let me make this K just to be like a spring. Some damping function, V damp, as a function of X dot. And a spring can have any, a spring is anything that produces a force as a function of X. A damper is anything that produces a force as a function of X dot. Right? And so if this is linear, if these are constants, so mx double dot plus b x dot plus kx equals the driving force F. So this is plus F. Then that's your typical second order oscillator, mass spring damper system. Second order because you got two derivatives there. So your state vector is x and x dot. Does that all make sense? Yes?
So just some fundamental question. How do you define oscillator? Like a living cycle behavior or?
Something that goes back and forth.
Because for the case on the left hand side, the x will never go back to
right,
the same.
So your state's not oscillating, but your output is.
Okay.
Your state's just going to infinity.
Okay.
Right. But in just loosely speaking, what you would need for running in order to locomote across the ground is you need to cycle through your appendages. So a wheel just needs to spin. This is pretty much the equation of a wheel, right? The angle of the wheel just keeps spinning. If you're at a constant velocity, and the output is any point on the wheel. Okay, so that's a linear mass spring damper. But in general, you can have a spring as long as you have X and the force from the spring. A restoring spring will you'll always be in these two quadrants where you just define 0 to be the rest length of the spring. If your spring dips down such that it's producing so this is drawn so that as you're compressing the spring, it pushes out. Okay. So I guess wouldn't be the negative sign here. But anyway, if I'll just draw it like that for convenience. If your spring ever dips down like that, then you've got problems where you're actually generating energy here. So it's kind of like a spring, kind of like a motor at that point. So let's assume for the time being that your spring is only restoring. It's conserving it. It's conservative. It's never adding energy. And let's assume for the time being that x dot versus of x dot. Your damper is only dissipative, only takes energy out of the system. And then a linear one is just where these are lines. Right?
So the lines are actually strictly increasing or?
It doesn't necessarily need to.
If with the spring, if it's not strictly increasing, then you get detents.
Yeah. For everything I'll be talking about now, it's strictly increasing, so that you don't have the detents.
But on that one, if you press it far enough, it will get stuck, and you have to actually push it in the other direction to make it snap back
right,
down.
and you could actually oscillate about another point here where there are detents. So let's just assume that it's
strictly increasing.
Yeah. Now it could be a stiffening spring, or it could be a softening spring, or stiffening in part and softening in some. But let's just say it's monotonic at least. Okay. Right, so it's easy to see why these things oscillate, right? You push it that way, your spring's pushing back, you let your spring accelerate it backwards, and with any sort of damping, if there's no driving, these things are gonna decay down. So if you give it an initial condition, if this is T, and X the position of the mass, then it's going to do some sort of decaying down. If you get rid of the damper, then it will to oscillate forever at its resonant frequency. And pretty straightforward. Right? Let's see. Okay, so now suppose, so you guys are familiar with Bode diagrams, probably, right? Anyone not here? Bode diagram?
But go ahead.
Okay. So let's take the linear mass spring damper and talk about Bode diagrams. So for this guy, what you then assume in doing a Bode diagram is that your driving function is some amplitude, the sine or cosine wave, times some frequency. So if we do 2 pi, f is in radians per second, or sorry, f would be in hertz then. Put the 2 pi in there. So we're going to drive this system with a force that's sinusoidal.
So it's basically a measure of how resonant it is at certain frequencies.
Okay. So if we take this system and give it a start and let it go, it's going to go at some frequency and damp out, right? If you go and measure the frequency at which it oscillates, that's your resonant frequency. So if we look at, put frequency here, at your resonance frequency, if you look at what the amplitude is going to be, the amplitude of the output, so amplitude of x, so that's just the peak that x takes on the output. At your resonant frequency for a given driving frequency, you can get some sort of amplitude. And if you're driving this too slowly, if you're just going really slowly, let's see here. So your Bode diagram is going to look something like this. Okay. So at resonance, you're going to get a large oscillation. So
it doesn't go below 0, does it?
well, this isn't 0. Sorry.
Bode scale is log.
It's a log scale.
0. Yeah, log. So zeros.
Okay, way down
Down
there.
there.
Okay.
Right, so if you take spring and find its resonance frequency, you can get, for very small amplitude of the input, you get high amplitude of the output. Okay?
Well, that's at resonance, but at extremely
resonance.
low frequency.
Yep. So now at low frequencies, it'll just kind of move with you. If I can move slow enough, so it's not, the amplitude is pretty low. And then at really high frequencies, the amplitude's low. But at just the right frequency, I can move my hand just a very little bit, and I get a large output. So that's at resonance. And then at low frequency, for this, it's kind of different because I'm putting in a position here, really. But the position, how much it moves on the output at really low frequency is going to be exactly how much I move the input. So it's going to be 1 at low frequencies, or 0 decibels. And then at high frequencies, it's pretty much going to be nothing. If you can do this super fast, the output really won't move at all. Okay? But for a linear system, the input and the output will be the same frequency at steady state. So if F is a certain input like this, then the output will be the same frequency. It might be phase delayed, and it might be amplified or not, but it's going to be the same exact frequency. Okay. All right, so that makes sense? Okay, so this is your typical Bode diagram, and you can do them either log scale, or if we don't do it log scale, then let's not do it log scale. Let's have this be 0. So this will just kind of go like that. Okay? And normally in a Bode diagram for a linear system, you're drawing the amplitude of the output divided by the amplitude of the input. Okay? But we're going to do it a little bit differently here for nonlinear systems. We're going to draw a few curves at different input amplitude and just draw the output amplitude. So here, if the input's 1 and the output's 1, but then if we drive it at 2 on the input, then you're going to get the same exact thing. It's just going to be twice as tall. Okay? And and etc. You go at 4. Amplitude of input. And that's kind of what you mean by a linear system, is if you linearly scale the input, you'll linearly scale the output. You scale the input by, if you double the input, you double the output, etc. All right, makes sense?
So there's multiple uses for linear here. A linear system gives you the scale the input, you scale the output, but this is also assuming a linear spring, because you get weirdness when you start.
Right, by linear it means everything's linear. The constant mass, constant damping, constant spring, and the input is just a cosine or sine. Pretty much, yeah, in the mathy terms, everything has to have a Laplace transform. So you can also analyze linear systems that have step inputs, because the step input has a Laplace transform. It's linear in that if I apply that, I get some output. If I apply double that, I'm going to get double the output, and everything works nicely. Okay, now if you want a linear oscillator to oscillate without adding any energy to it, how can you do that? Without adding anything nonlinear.
You can change the dampening or the...
You just take if you take the damping away, if you take the force away, and take the damping away, you can't have anything that takes energy out of the system. Everything has to be conservative. And then what you're going to get is, this won't die out, it'll just go forever. But you can't really change the frequency, and if all of a sudden there's a disturbance, like right here, and somebody bumps it up to there, then you're going to get twice the amplitude. If somebody pumps it down halfway, you're going to get half the amplitude. And so if you actually want to drive an oscillator, you have to start adding nonlinear effects to it. Or add some sort of feedback controller that... No, but even then I think the feedback would end up being nonlinear.
Would it help to say that if you made the damping coefficient B positive instead of negative to add energy instead of...
Well, then it would blow up.
Right, it would blow up.
Yep. So if you make B positive, it just blows up. B is 0, it'll oscillate forever. But in order to actually sustain an oscillation at a certain amplitude, at a desired amplitude, you have to start adding nonlinearities to it. All right, so go to nonlinear oscillators. And so let me jump to, all the fast runner guys have probably seen this slide 100 times. And what I'm going to try to do, it took me a while to actually understand it all the last few weeks. So I'll kind of go over what's going on. But, so, okay, so let's consider the case now where we have a hardening spring. So whereas this is a linear spring, a hardening spring is going to be something that looks like this. That's X and F spring. Okay. So you have a hardening spring. And real simple one to use is just F equals kx cubed instead of kx. Okay. And yes, let's consider that. All right. So for low amplitude, low displacement of the mass, the spring's going to be really loose, right? In fact, sorry, try to get that better. So the stiffness of the spring at low amplitude is really loose. There's hardly anything there. And then at high amplitude, it gets stiffer and stiffer. Okay? So if you're to kind of linearize it about low frequency, low amplitude, that would be a real loose spring, which would mean that the resonant frequency of that system is really low. Right. So if you go back to if you drive it at a real low amplitude. So if this is the driving amplitude, and then this is the output amplitude. Or sorry, this is frequency, and this is the output amplitude, and this is at different input amplitudes. So so if you have like amplitude of 1, then there's going to be a low frequency resonance, and you can get something like that. As you increase the frequency, so you're driving at a certain amplitude, like about that much, and increase the frequency, and then go past the resonant point, and it comes down. So now if you drive at higher amplitude too, then your resonance is going to be higher, because out at that amplitude, your output is going to reach, instead of reaching a certain amplitude here, it'll reach out further, so now you're stiffer. So if it was a linear system, you'd have just a larger resonant, but with the nonlinear system, you still have a resonant looking curve. So it might look like that. Okay? And then out at 4, something higher, it might be even further out. Okay? And that's what each of these curves here are, these orange ones. And I guess they kind of lean a bit more than I drew them. But let me get back to that. So anyway, this would be the resonant point you could drive at there, and here. Okay? Now, but what happens is, in order to oscillate at a higher frequency than where your resonant point is, you actually have to get to a higher amplitude, right? But if you're driving this thing at a smallish amplitude, and you start going at a higher frequency, what's going to happen is that frequency cannot sustain the oscillation, and you don't actually get this nice down curves. What happens is at this point it drops down, and then does the rest of the curve. And this point here, these things that look backwards upon the curves are actually unstable solutions. Okay, so that's here. So for example, this one here, these here are all unstable solutions. You can't actually find these points. Once you go at this amplitude, once you go higher than this frequency, you drop down right there and drive it out. And then what's neat is if you start decreasing the frequency again, you don't jump back up right here. You come back. So if I'm going out and then get too high frequency, it jumps down. And then if I come back, it'll kind of go like this. Does that make sense? Because you have to, in order to get back to, in resonating, you have to get to the amplitude that matches it. So you have to, in these systems with a stiffening spring, if you're driving it with a sinusoidal force, you have to slowly up your frequency in order to get to your resonance. You can't just jump there immediately, because otherwise you won't have the amplitude necessary to have the stiff spring. Does that make sense?
Mm-hmm.
So you increase the amplitude and the frequency slowly together in a certain relationship.
If you want to stay resonant the whole time, yes. If you want to stay resonant the whole time, you increase the amplitude and the frequency together. If you just wanted to get to this resonant point, and didn't care about being efficient, you could just drive this curve. Start with a large amplitude and increase the frequency. So you can either take that path to get to that point, or this path to get to that point. But you cannot take this path to get to that point. You can't oscillate really fast and increase the amplitude and get to that point. What you'd have to do is get the amplitude way beyond where that's a resonant, where you're actually at a resonant curve here at a really high amplitude. Then once you have resonance, then drop back down in amplitude, and it'll keep its resonance.
And you can't push straight up. Like the amplitude will not increase above a given. The amplitude will only increase to a point for a given frequency, unless you are ramping unless you're ramping the frequency.
Yeah. And what you find when you do simulations of these things is that at your resonant points, you're typically only doing positive work on the system and not doing negative work. And with these sinusoidal systems, you find that your driving force is aligned with your velocity, right? Because your input power, Pn, for a mass spring damper is going to be the force times the velocity. Okay. So what you want is, if this is the velocity, x dot as a function of time, it's going to be some oscillation. You want your force to be in phase with your velocity. If you're doing it sinusoidally, so that you're doing positive work, because if you weren't in phase, let's see here, when both are negative, let's see here, when one's positive and one's negative, so from here to there you'd be doing negative work, and from here's positive, negative, from there to there you'd be doing negative work. So you find that at resonance your velocity and force are in phase. Another way of saying that is that your position and force are 90 degrees out of phase, because your position is, your velocity is the derivative of position, of course. So if that's your velocity, highest velocity would be here. Maybe, probably didn't draw that right, but in this case, let's see here. Oh, sorry, that's supposed to be negative. All right, these don't correspond. You want your, let's see, I might want to be in front of it or behind it. When the velocity is positive, I want the force to be positive, so that's where I want the maximum force. So I want it to be like this. Okay. So you lead by 90 degrees, there's a 90 degrees phase between position and force, but an easier way to think about it is that your velocity and your force should have the same sign. If you're doing things sinusoidally, then they have to be aligned with each other at resonance. Does that make sense?
Is there some kind of energy pumping strategy to be more optimal to go to that point?
Well, it depends on how you're generating that energy, right? So think about if you have a swing, and for the most part it's a fairly linear oscillator except for the sign of the swing angle. A human pushing a kid on a swing stands in one place and pushes, right?
Right.
So that would be, in this graph, if green is position, when the velocity of the swing is 0 and it's all the way back there, that's when you'd want to push.
Right.
So as a human pushing a swing, what you do is wait till it reaches you and then start pushing that way. So for a certain amount of time. So this is kind of and then you're not going to run to the other side of the swing. You wait till it comes to you again. unless you have two people pushing. So that's your optimal driving for a swing.
And basically, the only rule that you have to follow is that you only push in the direction that it's moving.
Yeah.
As long as that's obeyed, it will.
Yeah.
Always do positive work.
Yeah, you're always doing positive work. It will find that resonant curve and then just ride that resonant curve out.
But it depends on, your efficiency is going to depend on your actuation system. So if you can produce high forces at low speed, like a human's arms,
Yeah.
you want to drive there. If you can produce forces better at high speed, like perhaps your electric motor, then you might want to drive here. Right? So it depends on your actuation
system. You can choose all that. You can choose all that based on your driver, as long as you're only pushing in the direction that is already moving, though. As far as the resonant system is concerned, it's going to be maximally efficient.
But it depends where your losses are. So for like a motor that has I square R losses, you probably want to minimize current. So there you probably want to be pushing when it's fast with low force, if you can. So where with a hydraulic system that has like a constant pressure source, there you can get pressure for free, but velocity costs you. So there you want to do what the human does pushing a swing, is only push when it's at low velocity, but with large force.
So ideally, you would push right along with the velocity. If it's going fast, you're going to push harder.
Well, again, it depends on your energy source. You don't have to be sinusoidal with it.
Right.
That doesn't really matter. As long as you're only pumping in energy in the direction that it's already going, you're doing only positive work.
Yep.
You can choose what your actual impulses, and not like instantaneous impulses, but your actual inputs of energy look like based on what your driver is. The resonant system, though, doesn't care at all where that is, as long as it's in the correct direction.
Oh, that's agreed. But when I said ideal, I wasn't considering optimization of a particular physical system with its limitations and power curves. I was just saying in the ideal case for the simple math, the force of driving is proportional to the velocity.
That's one simple.
I don't think it even matters.
That's just the ideal.
But it shouldn't. Yeah.
But it's
You
not
could
necessarily
give it a square wave just as easily as a sine wave in force, and it would still be optimally efficient.
Okay, so I've got some simulations of this that are instructive, but they might be hard to see, but hopefully you can see what's going on here.
I think I'm way early for tonight. The Innovation Coast meeting from Stephanie tonight.
Okay, and that'll probably be on me building.
Okay.
So just walk up the street.
Okay, so here's just a mess. And I apologize because of the size of the screen here, the graphs are gonna look really crappy. But so if I set this up, so F here is the driving amplitude. So here's with an amplitude of 1. And this has the nonlinear power of 3 spring. So you can see kind of and what it's doing is it's an amplitude of 1. It's ramping up the frequency and then ramping down the frequency.
So why is the ground moving?
Because I'm Dollying.
Dolly tracking here.
He's tracking.
Oh, wow. Okay.
All right. So you see it starts out slow, gets to about here. And this spring is such that it doesn't start stiffening to about here. Okay, just so you can visually see what's going on.
Is there a way we could see a graph of position versus time and position versus velocity?
Yeah, I've got these. It's just so the top one is position versus time.
The phase plot on top?
Yeah, so if you look at, this is the phase plot, so it started out, it's going out, as it hits resonant, it'll have the highest one, and then it'll come back in as it goes really high frequency. But this plot here you can see as this is the frequency versus the amplitude. You can see here it was just riding up this curve, and this is where it's going to drop off. So now it's going to be too high of a frequency for the amplitude I'm giving it. And you see it spiraling in.
Okay, if anyone's new to phase plots, that's position versus velocity. On the
Yeah,
top.
sorry, this is position versus velocity. And then this is the kind of the Bode diagram like thing, which is frequency versus amplitude. So you saw it grew up the curve, and then drop down, and then it'll just kind of stay out here, and then when you decrease the frequency, it'll come back here and not come back up to a lower frequency. Okay, so driving, the point I want to make is driving these things with a sinusoidal input as a function of time is tricky to stay at resonance, because if you go a little bit above the resonant frequency, you drop off. So you have to stay a little bit below it if you drive it.
So basically, you want whatever driving force you're using to look at what it's currently doing and adjust based on that.
Yeah. So here it is coming back up the curve. And you see, if you watch the amplitude of this, it's still pretty small until you get back to where you can be kind of resonant again, and then it'll spiral back up. So you get this hysteresis curve.
In the dead zone, there's a region to the right of the breaking wave where you can't be in that intermediate.
Yeah, and the dead zone, so there's unstable solutions that would be right here that you could drive it, but they're unstable. They jump either up or down. So does that make sense? See how that's... And then this simulation is checked in. It's just called nonlinear oscillator. So what we were doing is going along, hit this point here, jump down, went out, and then came back up, and get back in there. Okay, so that's what this curve is all about. There's, for a given amplitude, that's each of these orange ones. If you just sweep the frequencies, they're each going to have a different resonant frequency. And so if you want to be at resonance throughout it, you have to increase the amplitude and the frequency along this blue line. If you're to the right of the blue line, you'll fall off. I mean, there's a little bit of wiggle room with these, but not much. So if you try to climb this here, you can't. So it's safer to climb it on the left of the line.
I would say that the orange curves toward the bottom are kind of shallow on the left side and right side of the blue line, so they'd be fine. But once the slope goes vertical or beyond,
Right.
like overhanging, then you definitely fall.
Yeah, here you can just go up and down. Here you can go up and down. Right, but if you try to be right to the right of this blue line, then you'll fall off. Okay.
But again, all that's assuming that you're driving it with just a simple time-based sinusoid.
If you're driving it with a time-based sinusoid.
If you have a driver that pays attention to what it's actually doing and only inputs energy, then you don't
Exactly.
drop off that curve.
Yep. And yeah. Okay. So, oops. All right. So you guys seen this video? So this is Johnny with the stiffening springs. So as the amplitude increases and engages more rulers, you get stiffer and stiffer. So at low amplitude, you'll have a low frequency oscillation. Then at higher amplitude, it'll have a much higher frequency amplitude, much higher frequency. And Johnny will be driving it. He has feedback, so he's doing what it takes to. He's not just a wind-up toy that's staying on a clock. So he's able to stay resonant up to the end, but then at the end it's kind of hard to maintain it. It's such a high. Oops.
measuring from the photo, my fists, my hands on the end of the block there, moved starting at about a little less than an inch and moved about 1.5 inches, maybe 2. So the amplitude did increase with the frequency there. The tip of the ruler moved 6 feet
Fantastic.
on each swing. Back. So, that was a nice
Okay, we'll wait for that to come
amplification.
back. Okay, so Nick's been hinting at that you just have to add positive energy. So let's look at that. So, okay. All right, so I guess the spring I was using in there was actually alpha x plus beta x cubed. So that it doesn't have zero slope. It has a small slope at the beginning and then a greater slope. Okay, so if you write out the full equations of motion, if you set m equals to, this is kind of just sidebar but important, if you set m equal to 1 and have the spring like that, then your equations of motion are going to be x double dot plus the damping, which call it gamma here, x dot plus alpha x plus beta x cubed equals f cosine omega t. That's what you just saw on that simulation, and that's what's called a Duffing amplifier. Okay, and so it's equivalent to a unit mass, a spring that's alpha x plus beta x cubed, a damping with damping proportionality gamma constant, and then a driven Duffing amplifier is one where you drive it like this. Okay, so this is one of the amplifiers you see a lot of places, but it's exactly a mass spring damper with a stiffening spring. Okay, but we want to avoid doing this because of the reasons of dropping off of the resonant crest curve. It's just too finicky. So when we talk about, here's another example. When Chris and Johnny, you guys did this one, right?
Actually, I did this back with Matt Bellman.
Oh, Matt Bellman, okay. So this was kind of the same thing, but with a 2-joint link where you're driving it, and they drove it kind of how I'll be talking about here, where you, instead of giving it a sinusoidal input, you drive it based on the phase driving. So try to stay in phase with the velocity or 90 degrees out of phase with the position. Okay, so in driving an oscillator, here's really what's essential. Is when you have too little energy, or when the oscillation is too small for you, then add energy. And when it's oscillating too much, take energy out. Okay? So let's see how we can do that. So let's look at the Duffing amplifier, but instead of driving it that way, let's just drive it instead with some curve where when the velocity is positive, you just give it some force, and when the velocity is negative, you give it a negative force. Okay. And in fact,
They'd just be straight lines.
you could just do it like that. So anything will work, right? Just the key thing is that you're always doing positive work. And I apologize now, when I was drawing the damper, it should have been like that. Fixed up. Right, the damper is always doing negative work. So you want your driver to always do positive work. And if you do that with this system, by varying the amplitude of this, I've been calling this throttle now. If you just use a constant throttle, that's just a on-off throttle. By varying the amplitude of that, it'll increase both the frequency and amplitude of the driving. Okay? So I'll show a simple simulation of that. So pretty much for the simulation of that, all we do is go in here and where the controller is. Okay. So before, what was going on is ramping up that frequency up and down, and then the driving force was just F sine omega t. Okay. But I'm going to turn that off, and instead just say if the velocity is greater than 0. If the velocity is greater than 0, then set the driving force to be this variable called throttle. Otherwise, if it's less than 0, set the driving force to be negative throttle.
So one way to think of it is your max torque limit on your actuator, or your max force limit. If it's positive, just go to the positive limit. If it's negative, just go to the negative limit. And that would be the variable called throttle here.
Come on. Alright, well that's gonna run. Talk about what's gonna happen here. So, so if you plot on the same graph, the damper, so you're gonna have some negative damping here. It's gonna be that curve. If you add these guys up, it's going to look like the effective overall damping is going to look like that, right? Mm-hmm. So you see for x dot between here and here, here you're doing overall your drive minus the damping. Your drive's doing this positive work, the damping's doing this negative work. From here to here, the net effect is going to be positive energy, and from there to there, and then outside of here, out here, is going to be negative energy. So in this region, from the velocity from here to here, you're adding energy to the system overall. Velocity out here, you're taking energy out, so it's going to achieve some equilibrium where the average velocity in some sense is that velocity, and that's why it's a stable oscillation.
So if you're to the right of that point, the attractor pulls you back to it from the right, and if you're to the left of it, or I mean lesser amplitude or greater amplitude really, because it's symmetrical.
So here's a throttle of 1, and you see it doing certain frequency. Now if I increase the throttle to 2, both the amplitude and the frequency will increase. So if you zoom in here where I changed from 1 to 2, So in this one, the frequency is a little less subtle, a little more subtle. You see the. So here clearly the amplitude went up, and the frequency went up a little bit. Let me just sweep through some. Here. So if I do let me do a throttle 0.1. So you see kind of how low frequency that is.
What's on that second graph there?
Which one?
The second one from the top?
I ignore that one for this one. That was when I was driving it before.
Could we just delete it and make more room in the face
Yep.
place, or not worry about it?
Yep. Okay. So there clearly you see the amplitude goes up and the frequency goes up a little bit.
So the peaks occur closer together in time at the higher amplitude.
And then then you see the driving force in red is just the square wave we were talking about. So when the velocity is positive, it's a positive driving. When the velocity is negative, it's positive driving. And so you can do real simple driving to get your oscillator. You don't have to. But here's the key: is that as long as with the mass spring damper system, at least with the mass spring damper with the stiffening spring, at least, but maybe in more cases, if you look at the velocity x dot, that as long as you have the conditions such that inside overall you're adding energy from here to here, and out here you're removing energy, negative energy out here, doing negative power up here and positive power in here, then you'll get a stable oscillation. Okay? So there's a number of ways you can do that. But if you assume that you have linear damping there, so this is x dot and the force. If you assume that you have linear damping, then all you need to do is make sure that let's see here, that in some region here, so this is that your total force is above the curve and below. Well, let's see here. If we let's draw, this is a way of looking at it. Draw the natural damping this way, and in fact, let's be more general. Let's say that the natural damping does something like this. Okay, but I drew it positive here just so that we worry about where these lines intersect. So with the positive drive, with the square driving, you see that in here the driving is greater than the damping, and in here it is. So you're doing positive work, and out here you're doing negative work. As long as you have that. As long as you have that going on for you, then you get a stable oscillation with a stiffening spring. So you don't need to do that. What you could do, and this is the one Johnny likes showing for when your damping is air resistance, your damping is nonlinear stiffening, or nonlinear with greater than power than 1. Here you could do driving that's linear. And here you'd be doing your positive work. Now here you'd be doing negative. Here you'd be doing positive, and here you'd be doing negative. Okay. So the equations for that would be, you have unit mass x double dot, but instead of linear damping, you had some gamma x dot times x dot. So this is what you'd see with air resistance or water resistance or something like that, a square law, where you got to do the absolute value and not absolute value just so you get the sign right. Now another way of writing that is sine x dot times x dot squared. Okay, if that's your damping, And then you have this a stiffening spring. And if you drive that using some gain times x dot. So a linear drive with a square damping gives you the same effect. So you'd be, if you're oscillating inside here, it'll go outside, and if you're oscillating outside, it'll come inside.
So square damping would be order 0 and the line would be order 1. And if you have something squared and you're driving with a line, the squared is higher order. So as long as it gets greater, farther away from the origin, at some point that would be your steady state amplitude.
Yeah. So as long as the natural damping takes out more energy as you get higher velocity than what you're putting in, and as long as you're putting in more than the natural damping's taking out below that velocity, then you can get resonance. And the way we've kind of been saying that is damping has to be higher order than the driving to achieve a stable oscillation. Right. So if you have a line, then something that's second order will intersect the line like that. So that's what you need. If the damping is first order, then you need second order or higher.
And it doesn't have to be integer.
Or sorry, if the damping is second order, then the driving has to be lower than second order.
Right.
First order.
So usually there's a friction, right? So would that break a deal?
So friction is typically thought of if you have
Coulomb friction.
Coulomb friction.
Coulomb friction.
So there you're going to have a force. So then the damping is going to be something like this.
Right.
Okay. And so there, you need to at least get past it.
I see. Yeah.
So something, anything like, again, just the constant force would do it for you.
Yeah.
It'd be like trying to drive a brick on a table. You'd have to push and pull it enough to overcome the static friction transition.
Yeah. But if you did anything, pretty much any curve that's greater than it at some position, and that's lower than it at the other position, so that you're doing positive work there and negative work there, will give you oscillation. Now those are sufficient conditions. They're not necessary. You could probably, keep doing this, and then it'll just find different regions of oscillation.
Yeah, general case.
But if you do have this condition, then it's nice and pretty. Okay. So this would be the equations again for that, and the only difference here being that you're driving linearly and that the damping is square. Okay. And you can play with all these parameters to get different shapes and whatnot. All I'm trying to cover today is what is the fundamentals. If you want a nonlinear oscillator that increases in amplitude with increasing frequency, which is what animals do when they're running. As they run faster, their stride length both goes up in frequency and in length. So that's kind of what we want. Then you need a stiffening spring, and then to make it resonate, to make it oscillate without forcing a cosine function as a function of t, then you can do so by just making sure that your drive as a function of velocity gives you positive work net at low velocities and takes energy out overall at high velocities. As long as you have that, then you've got your nonlinear oscillator that does what we want to do. Does that make sense? Okay, so I wanted to also show you, whenever you look up like oscillators, you always hear about Vanderpool oscillators too. So I want to just look at what a Vanderpool oscillator is with respect to what we're talking about here. I think that's all I had. Okay, so a Vanderpool oscillator. So again, this is a Duffing oscillator, and that's just the driving part, but we're saying we're not going to drive it that way. We'll just put more generally close to F. Duffing oscillator. Vanderpool is, make sure I get it right here.
Damping is nonlinear, right?
The damping is a function of position. So it's,
So that would rotate the whole phase plot 90 degrees, but basically you'll have the same shape.
so you get x double dot
Is that
plus x squared minus 1 x dot plus squared x. Okay, so this is an x squared. All right. Imagine that wasn't there. Then you'd have a unit mass, x double dot, plus mu times x dot, so a linear spring, or a linear damper, plus omega naught squared times x, so linear spring. Okay? But now what you do is say, okay, make the damping, instead of just making the damping a constant times velocity, make that, essentially change that constant dependent upon what x is. So if you look at the phase plot, here what we're saying is if x is 1, then there's no damping. If the magnitude of x, if x is 1, there's no damping. And if x is greater than 1, then there will be damping. And if x is less than 1, you're driving. So as that mass is going back and forth, and the mass is going back and forth. So here you're actually accelerating it out until it gets there. Then you're doing deceleration. Right, so decelerate here, dependent in whatever direction you're going. So here accelerate, here decelerate. And you can see why that would oscillate too. So once you get moving a little bit, just keep increasing, your velocity, speed up, speed up, speed up, and whoa, put on your brakes. But now your spring's pulling you back, and then whoa, accelerate, and you get oscillation.
Would that be corresponding to like a bistable switch, where it draws you home, but when you get close to home, it pushes you away from the exact center to two stable locations either side?
No, I mean it's not bistable. It's still just going to be an oscillator.
Okay.
If you look at
Because it's damping only.
if you look at x and x dot,
Yeah, because it's damping only, it's not the spring forces. Okay.
So the way you just described that, I'm seeing the damper putting in energy.
the damper, this is a damper when x is greater than 1, and it's a motor when x is less than 1.
Okay.
Okay, because you see how the so if you look at, suppose x dot is 0. If x dot is 0, then you just have a spring, right? So if we look at the way this is going to happen is you're just going to, see here. Is that right? So if x is positive, it's just going to pull you back towards 0. So anywhere x is 0, anywhere x dot is 0, you're just kind of perpendicular to here. And then when x is 0, then you're going to have negative damping. So this would be -1. So you're going to be driving when x is 0, kind of like that. Okay. And then between x being 1 and -1, you're actually adding energy to the system. And outside you're taking energy out. So you're going to get some sort of oscillation.
I'd like to call attention to the upper right and the lower left diagonal corners, because that's where we're adding energy. If you were to draw an ellipse connecting the mid-segments of the box, the vector would have to be pointed outside the ellipse on those corners there, and that's why the phase plot gets those ears on the corners. Because we're adding energy on the diagonals, on the right, lower, left diagonal.
Well, you're adding energy anywhere between here and here.
Right. So it's going to tend to climb in amplitude there.
Oh, I see what you're saying. So it's kind of going to go like that.
Yeah.
Right.
and it's gonna go like that.
Okay, yeah. Whereas if there was just no damping at all, you'd get circles.
Right.
You'd just be oscillating between X and X dot. So here they're gonna kind of look, I'm guessing, kind of more like this.
Right, and in the opposite diagonal quadrants, it'll be collapsing a little bit.
And then if you're outside of that, it's gonna come back into it. And if you're inside of it, it's gonna spiral around to it.
So we get ears stretching on the right, upper right, lower left diagonal, and we kind of get a flattening on the opposite diagonal.
But I just wanted to bring that up because you always see Vanderpool oscillators, and I never really understood, well, what's it actually doing? This is the way to interpret it, I think, is that it's a mass spring damper, where the damper switches from a motor to a spring, depending if you're inside or outside X equals 1. That I don't think we should shoot for with Fast Runner, because you're alternating between positive work. Here you're doing positive work, and here you're doing negative work. So you're just wasting energy. You always want to only be doing positive work if possible. That's why we think a Duffing amplifier is a better one to look at, because this is damping that exists in the system. You can't do anything about that. You'd like it to be 0, but it's not. And you're actually driving. You want to only drive. You only want to do positive work when you're driving, not do something like this where you're doing alternating between positive and negative work. But it is also a way you can make an amplifier. You just pretty much need some region of state space. In fact, I bet you could come up with a general amplifier where if you just took X and X dot and just said, so with the Duffing oscillator, you say you're doing positive work from here to here and negative work outside it, or no, have the motor do no work here or less work than the damper's doing. So that's kind of what your Duffing oscillator does, is positive work in there, negative here. Vanderpool oscillator looks at X to see if it's going to do positive work between here and negative work outside. But you could easily come up with an amplifier that just takes some arbitrary section of state space and says, okay, just make sure you're doing positive work in there and you're doing negative work out there, and then you'll be stable. It's not going to stabilize to in here. It's going to take some path that'll sometimes do positive work, sometimes do negative work. But out here you'll be doing negative work, and then out here you'll be kind of compressing these circles, and then here you'll be doing positive work, so you'll be pushing out the circle.
So what Chris and I developed for an arbitrary thing is, I think a classic oscillator, I don't know, I'd have to check the literature, it might not have been developed yet, but where the Vanderpool changes the damping based on X to either drive or diminish for a steady state amplitude. We used a bistable spring in addition to a restoring greater nonlinear spring. Mm-hmm. And so by shaping that contour, we got the behavior that we wanted, and we can even modulate that.
Right.
But I don't know if that's a new class of oscillator in the mathematical literature, in which case we should claim it, or if someone's done it, and we should look at that.
Let's make running robots.
Right.
Not worry about oscillators. Except that we need oscillators.
Right.
So in summary, the main points are that if you want the amplitude to increase as frequency increases, that you have to have a stiffening spring in your system, something that looks like a stiffening spring in your system, which is what we want for running. And that you can make them oscillate by driving it with the cosine as a function of time, but that's not good if you want to stay at resonant, because if you're not perfect, you'll fall off the resonant crest curve. So instead, it's better to try to do some sort of phase driving, and in general, by phase driving, we mean just do positive work when possible. Try to only do positive work. Infinite number of ways you can do that, but as long as inside some region of your state space, you're adding energy, and outside that region, you're subtracting energy. If you have a mass spring damper system, the system will find something that doesn't blow up and doesn't shrink to 0. It'll keep on oscillating. Now, whether or not that oscillation is a limit cycle or something chaotic is a whole nother ball of worms. One nice thing though about a Duffing amplifier or a Vanderpool oscillator is if it's only second order, so you have just X dot and X as your state variables, you can't have chaos with a second order system. You need 3 variables at least to have chaos. If you're driving as a function of time, you essentially get that third variable, and so your driven Duffing amplifier can be chaotic. But if your force is just a function of your position or velocity, like it is in a Vanderpool oscillator or the Duffing amplifier plus driving like we were showing, then it won't be chaotic. But that doesn't really mean much because we actually use these by adding them to something else with a lot of degrees of freedom, so you can get chaos really fast. It's just kind of a side note. Any questions?
That was probably the clearest explanation of Vanderpool that I've seen. That was really clarifying.
Well, my drawing is so clear that how could it not?
So, as an outsider of FastRunner, can you remind me the goal? Like, it sounds like you try to use passive mechanism design instead of programmable motors.
For the most part, you have to have at least one motor in there. But kind of where all this fits in with FastRunner is, number one, that you need some sort of oscillator. As I showed at the beginning, even if you're a wheel, you're an oscillator. So you might as well.
But when you say oscillator, you refer to hardware oscillator or even program?
Well, it could be either hardware or programmatic.
Okay.
What we're trying to do in FastRunner is, this is a very simplified version. What we're trying to do is have a bunch of mass, a bunch of springs, a bunch of dampers because they're going to exist, and then drive one of the linkages such that you get nice nonlinear oscillation where the harder you drive it, the higher the frequency and the higher the amplitude the step is, and drive it in such a way that it just naturally finds these limit cycles rather than trying to force it with a sine wave on it. And this is probably the simplest abstract thing you can come up with that shows those features, right? So what we're trying to do in general with FastRunner is break out the 40 to 80 different little elements, one being nonlinear oscillators, go over them one at a time, and then assemble them back together.
Jerry, do you think it would help with Ting Peng's question if we distinguish between emulating a physical spring with programming, in which case we pay for the energy but we get the same result, and also about virtual damping where we withhold driving effort as though there were wind, things like that?
I don't know, does that?
Yeah, just try because from the study here, it seems like if you can, because programming is easier. If you just program the whole thing and make it working.
Right, yeah, no, in the FastRunner we want to make them all be physical elements so that you get the energetics for free.
Right. So actually you don't want damping, you want some kind of energy storage.
Well, right, but there's going to be damping no matter what. If there's not damping in your joints, there will be damping from wind resistance. And that's a square damping.
Right, but you don't want to add in damping unless it's already there.
Right. Virtual damping by withholding effort is okay, just don't drive it as hard as though the wind were blowing, right? But he's saying don't add physical dampers because that would destroy your energetics.
Right, we don't want to add physical dampers unless necessary to get stability, but wherever we can avoid it.
And we want to use physical springs to save the real energy.
Right. Yeah, because if you emulate a spring with a motor, you're not going to get the energy back very well, even if you have a regenerative brake or something. And then the other effect is that springs and dampers happen instantaneously. You don't have to worry about like control loop rates and stuff like that. You can have an infinitely stiff spring that you actually build works really well, whereas if you try to do one control-wise, it works horribly. Or a very stiff spring.
So an easy to remember rule of thumb is no virtual springs, but if you need them, virtual dampers. That way you maintain the energy. It's all about that's what it is.
Okay. Good. All right. And so I hope that all made sense. This was the easy one, probably the only simple one. And the only one that's kind of that you can do rigorously. Everything else gets kind of hand wavy.
Well, I like this development because presented this way, it opens up all the options. Drive it any way you care to, any way you can, as long as you're doing positive work.